In this video, we are going to talk about electricity and magnesium. So we are going to talk about electric field first. So this is the topic 5.1 of IB physics. For university physics, I will post more video about this topic to talk about them more detailedly. So here is a list of topics that we are going to introduce in this lecture. So the first one, we are going to talk about electric charge. So electric charge is a property of matters, and it can be either positive or negative. So positive, when we talk about positive charge, is usually refers to proton, and negative charge always refers to electron. So what allow matter to have charge is because of proton and electron. So we know matters are made of atoms. So here is atoms, and then you have some proton here, and then you will have some neutron here. And this here, proton and neutron together, they are called nucleus. And then you have electron that is orbiting around the proton. Around the nucleus. So this is electron, in which has a negative charge, and proton has a positive charge. So when the number of proton is greater than the number of electron, it's gonna be a positive charge, and it's gonna be a negative charge when number of proton is less than number of electron. And when number of proton is equal to the number of electron, we say it is neutral. So this is why some matters are negative charge, and some matters are positive charge, and some matters are neutral, meaning they have no charge. So proton has a positive charge, electron has a negative charge, and neutron has no charge. And another thing I want to talk about is about electric charge is this statement, like repel, opposite attract. So when you have two positive charge, a repulsive occur. So the two positive charge are gonna repel each other. Same thing with two negative charge, they're also gonna repel each other. But when you have one positive charge and one negative charge, an attractive force occur. So the positive charge and the negative charge, they're gonna attract each other. So this is like repel, opposite attract. So sign charge with opposite sign is gonna attract each other, and charge with the same sign is gonna repel each other. So in this case, a attractive force occurs, and here a repulsive force occurs. So from this statement here, we know that charges produce electric force, and this is very important. So charges produce electric force. So we talk about the number of proton, and the number of proton determines the charge of an atom. So when the number of proton is greater than the number of electron, object is gonna have a positive charge, and when number of proton is less than number of electron, object is gonna have a negative charge, and when both number are equal, object is gonna have a zero charge, so it's gonna be neutral. So in an atom, proton is part of the nucleus, so it does not move. What really moves is electron. An electron conduct current. Electron carries current when they move. So free electron carry current. And because of those free electron, matters can conduct current. And there is two main type of material. The first one is conductor, and the second one is insulator. Right. So conductor, they can conduct electricity because they have a lot of free electron. An insulator, they do not conduct electricity. Because there's no free electron. So some example of conductor is human body, graphite, and metals. An example of insulator is rubber, air, and glass. We know charges produce electric force, and we also know the number of proton and the number of electron determine their charge, and free electron is what carry current and make a material conductor or insulator. So now I would like to talk about property of charges. So the first property is very simple. So charges can be positive or negative. And negative is electron and positive is proton. Another property is that charges are quantized. Quantized means that the charge of an object can only be an integer multiple of their basic unit. And the basic unit of charges is Coulomb, which is represented by the letter C here. And the last property we are going to talk about is that charges is conserved. In a system. So let's say we have two objects, object 1 and object 2, and then they are stick together. Then object 1 and object 2 are a system. So the total charge of object 1 and object 2 are conserved. So the charge can be transferred from one object to another, but the total charge of the system is always conserved. So since we have talked about the basic unit of Coulomb, I would like to talk about them a little bit more. So we know everything is made of atoms. And atoms have three basic particles, which are proton, electron, and neutron. So their charge, usually we represent proton with the number of positive 1, electron is -1, neutron is 0 since it has no charge. But represent this in coulombs. Proton has a value of 1.6 times 10 to the -19th power coulombs. So 1 proton is equal to 1.6 times 10 to the -15th power coulomb. An electron has a volume of -1.6 times 10 to the -19th power. A neutron has no charge, so 0 coulombs. And the symbol, their symbol, proton is always represented by the letter E or E plus. Electron is represented by E minus. Neutron is represented by E0 since it has no charge. And their mass. Proton, mass in kilogram. Proton has a mass of 1.67 times 10 to the -27th power. Electron has a charge of 9.11 times 10 to the -31st power. And neutron has a charge of 1.67 times 10 to the -27th power. So we talk about that electron is the current carrier. Because of electron, material are able to conduct electricity. And this was proved by a scientist called Thomas Dewar and his famous experiments, the Thomas-Dewar experiment. So let's say here is a metal. An electron will be free to move inside the metals because they carry current, while proton will be in a fixed place. So if the metal is suddenly accelerated, then what happens is that the electron will fall back to here, will fall back to the right. Then there will be an excess negative charge on the back of the metals. Right? So it will be something like this. So the metal is suddenly accelerated with acceleration of a. Then the electron will fall back, while proton remain in fixed place. So here will be a excess negative charge. And this experiment was done by Thomas Dewar, and he measures the excess negative charge to prove that electron is what carries current. So since electron carries current, and they attract proton, and since charges with opposite sign attract each other, and with same sign repel each other, electric force is produced, and this force is calculated by Coulomb's law. So Coulomb's law says the following: electric force is equal to Coulomb constant times Q1, so charge 1, times charge 2 over R squared. So this is Coulomb's law. So F here is electric force. And K is Coulomb constant. So let me write it down here to save more space. In which has a volume of 8.99 times 10 to the 9th power. Q1 is the charge of object 1. So I'm just gonna write M1. Q2 is the charge of object 2. And R is the distance between object 1 and object 2. Right. So this is Coulomb's law. So we know force has a SI unit of Newton. R has a SI unit of meter square. Charge, they all have a base unit of Coulomb. Right. So Newton is equal to the unit of K times Coulomb square over meter square. So the unit of K is gonna be equal to Newton times meter square over Coulomb square. So this is equal to K, the unit of K, Coulomb constant. So Coulomb's law says electric force is equal to Coulomb constant times charge 1 times charge 2 over R squared. And this is Coulomb constant. So K, Coulomb constant, is also equal to 1 over 4 pi times ellipson. So ellipson here is electric constant. In which has a volume of 8.99 times 10 to the 9th power. So now Coulomb's law, F is equal to K times Q1 times Q2 over R squared is also equal to 1 over 4 pi ellipson times Q1 times Q2 over R squared. So this is Coulomb's law. So when you are solving a problem, it is always safer to calculate the magnitude of the force first and then to determine its direction, because the volume of the force might be negative, but the direction might be rightward or upward, which is represented by a positive sign. So it is always safer to calculate the magnitude first. For example, let's say here is a positive charge and here is a negative charge. So a attractive force occurs between the charges. So the positive charge is going to receive a leftward force of F1. And the negative charge is going to receive, the positive charge is going to receive a rightward force of F1, and the negative charge is going to receive a leftward force of F2. So for the positive charge, F1 point rightward. So represented by a positive sign. However, if you plug in the volume into Coulomb's equation, so F is equal to Q1 times Q2 over R squared times Coulomb constant. We know that K is a positive volume. Charge 1, let's say, is the positive charge, is also a positive charge. Electron has a negative charge, so the negative charge here. And R squared is also a positive charge. So the volume is still going to be negative. Right? But with the direction, it's going to be a positive sign. So it is always safer to take the magnitude first. And then to determine its direction, to determine the sign of the quantity. So now let's talk about electric field. electrofield is defined as force per charge, which is equal to F over Q. So Q represents the charge, and this represents electrofield. And electrofield is a vector quantity. So we know electrofield is equal to force over charge, and force is equal to, let's say the test charge is charge 1. Charge 1 times charge 2 over R squared over charge 1. So this is equal to K times Q2 over R squared. So what this represents is the following. So let's say you have a positive charge here, right? And the electrofield is gonna radiate outward. And the arrow is gonna decrease in size because the electro force decreases. It's gonna radiate in all directions. Now, what happens if you have a charge here? Right. What is the force per charge? So what is the force per Q1? So we know, let's say this charge is Q2. So we know the force is equal to K Q1 Q2 over R squared. So A is gonna be equal to F over the test charge Q1, which is equal to K Q2 over R squared. So this is what electrofield represents. So different charge have different electrofield. So for a positive charge, electrofield is gonna radiate outward. And for a negative charge, electrofield is gonna radiate inward. And the size of the arrow will decreases. Right. So this is the electrofield for a negative charge and for a positive charge. So let me draw a line here. Then what's gonna be the electrofield between the positive charge and the negative charge? So you know, for positive charge and negative charge, they're gonna attract each other, right? So the electrofield will become something like this. It's gonna become something like this, and this is also gonna curve a little bit. Same thing here. So the electrofield between a positive charge and a negative charge will become the following. So this is electrofield between a positive charge and a negative charge. And the direction of electrofield at any point is a tangent line. And this is called the field vector. Okay. Then we also know if two charges with the same sign, they're gonna repel each other. So the electrofield between two positive charges is gonna look something like this. And this does make sense, right? Because positive charge is going to have an electrophile radiate outward, and two positive charge is going to repel each other. So originally the electrophile is something like this, and because it repels each other, it curves a little bit, right? So this is the electrophile between two positive charge. Now, what about the electrophile between two negative charge? So we know electrophile of negative charge radiate inward, and two negative charge is going to repel each other. So here it's going to have a electrophile radiate inward. And here you're also going to have a electrophile radiate inward. But because it repel each other, so it's going to curve a little bit. So it's going to be something look like this. Right. And same thing down here. So this is electrophile between two negative charge. So now let's do a few example of electrophile. So let's say here is a positive charge of Q1 and another charge of Q2, and the distance between the charge is 2 meters. So what is the electrophile of Q2 caused by Q1? So electrophile is equal to the force over the test charge. So in this case Q2, which is equal to K Q1 Q2 over R squared over Q2. So this is equal to K Q1 over R squared. So let's say Q1 has a volume of 1 coulombs. And R is going to be equal to 2 meters. So this is going to be equal to K over 4. What's a unit of Newton per Coulomb? So what is the direction of electrophile of charge 2? So we know positive charge is going to radiate outward. So the electrophile is going to point to the right direction. So electrophile must be a positive volume, right? But what happens if we switch the position of charge 1 and charge 2? So let's say here is charge 2. And here is charge 1, in which has a volume of 1 coulomb. And the distance between the two charges is 2 meters. So we know electrophile is equal to force over the test charge, so over Q2, which is equal to K times Q1 over R squared, which is equal to K over 4. And because charge 1 is a positive charge, electrophile is going to radiate outward. So the electrophile of charge 2 is going to point to leftward, which is represented by a negative sign. So electrophile is equal to negative K over 4, with a unit of Newton per Coulomb. So just be careful with the direction of electrophile, because sometimes the volume of you calculate might not be consistent with the direction of electrophile. So it is always safer to determine the magnitude first and then to calculate direction. So we know free electron is what carries current, right? So free electron carries current. And this is why current I is calculated by the formula of Q over delta T, right? So current is the flow of electron. Or you can say is the rate of electron flow. Right. So I is equal to charge over delta T. So ampere is equal to coulombs over second. This is the unit of current. So how do we express current in terms of free electron? So let's say here is a metalware, and there's gonna be a lot of free electron inside the metalware. So let's say in t second, the free electron travel to this area, and this here has a length of delta L. So what we know is that the following: only electron, because electron flows here, and only electron flows in this volume. So the volume here, right? Only electron in this volume can conduct electricity. So the total volume is equal to area times delta L. So area is the bottom area here. And delta L, how do we express delta L? So we know electron is traveling at a velocity of v in delta t second. So delta L is going to be equal to velocity times delta t, right? So velocity times time is equal to displacement. So area times delta t times velocity is going to be equal to volume. Volume is represented by the letter capital V. And we also know that in the volume V, it has a charge of Q per unit volume. So let me write this down. Charge of Q per unit volume. So the total charge is going to be equal to N times Q times volume, which is equal to A times delta T times velocity, right? So N refers to a number of electrons. Charge refers to Q refers to charge. A is referred to area. Delta T refers to time. V is velocity of electron flow. Right. And we also know that charge is equal to Q over delta T. So this is going to be equal to N times Q times A times delta T over delta D, which is equal to A times Q times A times V. Right. So this is how we express current in terms of free electron. So whenever a charge is near another charge, it will always experience an electric force in general. So to move a charge Q from A to B, work must be done, right? So let's say this is Q, and this is another charge Q, and here is A, here's B. So move the charge from A to B, work must be done. Let's say here's Q1 actually. So the ratio of work done over Q is defined as voltage, or you can say potential difference. So potential difference is defined as the work done per unit charge to move from A to B. So to move from its initial position to its final position. So let me write this down. So potential difference is the work done per unit charge to move from its position, to move from its initial position 2 is final position. Right. Work over charge is equal is V, potential difference. So V has the SI unit of joule over coulombs, which is volt, represented by the letter V. Right. So from this equation here, you can also know that work done to move a charge from A to B is equal to the charge times is potential difference. So how can we prove this formula? So we learn from our previous knowledge, we know that work is equal to F times delta D. Right, so D is the displacement. So in this case, we're gonna rotate delta R. Right. So let's say this is charge 1, this is charge, and this is A, this is B, and move to this position. So here is delta R. So what we can say is the following: the force between charge 1 and charge is equal to K times Q1 times Q over R squared, where R is the distance between Q1 and Q2. And to calculate the work, you need to times delta R. Right? And this is going to be equal to work. But here, this part here is going to be equal to the electronvolt of charge Q. Right? So work is equal to K times Q1 over R1 times delta R, which is equal to electronvolt times delta R times Q. And this part here is defined as voltage, or you can say potential difference. Right. So work done is equal to charge times delta V. So delta V is voltage difference, is potential difference. And delta V is equal to electronvolt times delta R. Right. And this is where the formula of electronvolt comes from. And from this equation here, we know whenever there's a work done, electronvolts must also be present, right? So it is very important to realize this. And now let's do a quick example. The example is here. The work done on a moving charge is 2.0 microcoulombs. Between 2 point in electronvolt is 1.5 times 10 to the negative 4th joule. Determine the potential difference between the 2 points. So we know potential difference is equal to work done over charge per unit charge. So work done is equal to 1.5 times 10 to the negative 4th power over 2 times 10 to the negative 6 Coulomb. So convert microcoulomb to Coulomb into times 10 to the negative 6th power. And this should give us a volume of 0.75 times 10 squared, which is equal to 75 volt. Right. So this is the answer for this problem. It's pretty straightforward. But then scientists usually use joule to represent work done, the unit of work done. However, in micro level, the unit of joule is too large to express the quantity. So scientists invent another unit called electronvolt. Right. An electronvolt is defined as the following. Electronvolt is defined as when a charge equal to electron moves across a potential difference of 1 volt, right? So 1 electron volt is equal to the charge of electron is equal to 1.6 times 10 to the negative 19th coulombs times 1 volt. And this is equal to 1.6 times 10 to the negative 19th power joule, right? So joule is equal to coulomb times volt. And this is equal to 1 electron volt. So when 2 electrons moves across a potential difference of 1 volt, the work done is gonna be equal to what? So work done is equal to voltage times charge. So when 2 electrons moves across a potential of 1 volt, it's gonna be equal to 2 electron volt, right? The work done is gonna be equal to 2 electron volt because here, charge of an electron times 1 volt is equal to 1 electron. Charge of 1 electron times 1 potential difference of 1 volt is gonna be equal to 1 electron volt. So when 2 electron moves across a potential difference of 1 volt, it's gonna be equal to 2 electron volt. And when 3 electron moves across a potential difference, let's say 5 volt, it's gonna be equal to 15 electron volt, right? So this is how we define electron volt. And now let's do a simple example. Determine the speed of a proton that is accelerated from rest by a potential difference of 5.0 times 10 to the third power voltage. So we know work done is equal to voltage potential difference times charge. So how do we solve this problem is by using conservation of energy. So we know from conservation of energy, we know work done. Energy gain is equal to energy lost. So since the proton is brought to rest by a potential difference, then change in kinetic energy must be equal to the work done by the electrophile, by the potential difference, right? So now we can calculate the speed of the proton. So we know change in kinetic energy is equal to final kinetic energy minus initial kinetic energy. And since the proton is initially at rest, it has an initial velocity of 0 meters per second. So the kinetic energy, changing kinetic energy, is equal to final kinetic energy. So Q here should be a delta V times delta V is going to be equal to a half times mass times VF squared. So VF is going to be equal to 2 times the charge times potential difference over mass of a proton, and then you need to take the square root. And this should give you a result of 9.8 times 10 to the 5th power meter per second. So part B asks a proton with speed of 4.4 times 10 to the 5th power meter per second enter a region of electrophile directed in such a way that the proton is slows down. Determine the potential difference required to slow the proton down to half of its initial speed. So for this problem, we can use conservation of energy. So change in kinetic energy must be equal to work done by the electrophile, right? And here we know the final velocity is equal to half of its initial speed. So changing kinetic energy is going to be equal to a half time mass times a half time initial velocity squared minus initial velocity squared. So I'm going to take the magnitude. And this is equal to a half times 1/4 times VI squared minus VI squared. in which is equal to half times mass times 3 over 4 VI squared, and this is equal to A over 3 VI squared times mass. Right. So this is changing kinetic energy. And now we can plug in a number. So when you plug in a number, you should get a result of 1.2 times 10 to the negative 6th power. Right. So you can just plug in the initial velocity here. And you should get a number of this. So this is equal to changing kinetic energy. Right. So now we can calculate changing potential difference. So from this we know the potential difference is going to be equal to changing kinetic energy over a charge of a proton. Right. Oops. Oh, sorry, guys. Here should be negative 16. So changing kinetic energy is equal to 1.2 times 10 to the negative 16 joule. So potential difference is going to be equal to 1.2 times 10 to the negative 16th joule over charge of a proton. 1.6 times 10 to the negative 19th Coulomb, in which is equal to 750 volt. So this is the answer for part B.